Geography 243, Remote Sensing 1. Remote sensing, as we practice it in this course, is focused on the sensing of reflected and emitted electromagnetic radiation from the Earth's surface, principally by spaceborne platforms. This is a Landsat image that you're looking at here of O'Hare Airport and the Elk Grove Village Industrial Complex that's immediately west of that, west and north of that, that facility. Everything that we do in remote sensing is built upon over 100 years experience, well over 100 years experience with aerial photography, first starting in the 19th century, middle of the 19th century with balloon photography, kite photography, and ultimately aircraft photography in the 20th century. This is how, really how the maps that we have, the detailed maps of the United States and most of the rest of the world, were created through the use of cameras, film, and that technology. And so most of that, as it happens, came out of the military. This is the K-17 aerial camera that came from Fairchild, from the Fairchild Aircraft Company, beginning first in World War I, but then through World War II. And so these surplus cameras were used for most of the civilian photography that we have in our archive of photography. Photogrammetry that you reviewed from the text is the science of making measurements from principally photographs that have a particular geometry to them. It's illustrated here, that produces a map-like image on a photograph. It's map-like, it's not a map, the actual image itself, because of distortions in the image due to this geometry. And you can look at this and more or less tell what those distortions might be. They're terrain distortions, elevation distortions. There are distortions because of the placement in the image, radial distortions from the center of the image. So there's a number of different kinds of distortion in aerial images, and also in digital remotely sensed images that have to be dealt with as we start working with the raw data that's worked with mainly through the U.S. Geological Survey facilities that we get these data from. So this is a 10 by 10 contact print of an image in a black and white aerial photography or aerial photograph in Texas, and this gives us a sense of the kind of photography, millions of aerial photographs that were used to map the U.S. in great detail. So this is a photograph of a photogrammetrist at the Tennessee Valley Authority, working in conjunction with the U.S. Geological Survey in the 1930s, mapped in great detail the Tennessee Valley, which covered several states in the southeastern United States, and this was the first really major mapping project, civilian mapping project, where a large part of the country was mapped almost completely using photogrammetric techniques. So the stereoplotter is the instrument that allows us to make and map three-dimensional models of the terrain, of the Z value in the terrain. The X and the Y are also captured in this mapping process, but probably more importantly, I think, is the Z value, or the elevation value, that's obtained from using these mapping instruments. And they're, some variation of these are still in use, although more and more they're becoming automated, using automated stereo models. And so, this mapping relies on the collection of overlapping aerial images, and it still does. Even the stereo mapping systems that work from outer space work in the same way. It requires capture of overlapping aerial frames that give us a parallax view of the Earth's surface from these vertical aerial images. So again, we're focused back on that the geometry, the peculiar geometry of an aerial image, and what I guess the effects that this have on the image, and the really the ability that this gives us to do particular kinds of mapping, in particular three-dimensional stereo modeling and stereo mapping. So this is the process. This is figure 1.1 from your textbook, and this is the process as it exists. And so, you start with the sun. You have propagation of electromagnetic radiation. We usually use the wave model of radiation to understand that through the atmosphere, the different things that happen to it in the atmosphere. That would be B, what happens at the surface. Energy is either reflected or absorbed and re-emitted, or transmitted, usually through water. It goes back through the atmosphere, and then it's captured by some kind of remote sensing instrument, and then this data, either analog pictorial data or digital data, is then processed and combined with reference data. And we do various kinds of processing and analysis and interpretation, including visual and digital processing, and produce value-added information products that wind up on a table with a bunch of decision makers sitting around that table. So this is the whole process of remote sensing, and if you're trying to figure out where you are in the process, this is a good diagram to go back and look at any given time in the term. One of the fundamental principles that we work with is the notion of the wave model of electromagnetic radiation. And in this model, we make distinctions between different types of radiation based on their wavelength value. Now, this is a spectrum. In other words, it is not these are not sharp boundaries between colors that we can see. It is a smooth, more or less smooth transition from one type to another type. The visible spectrum has a very small range in the broad spectrum of electromagnetic radiation, ranging from about 0.4 micrometers to about 0.7 micrometers. Everything of a shorter wavelength than 0.4 we refer to as principally ultraviolet, and then you get into other categories of radiation as you move to shorter and shorter, higher energy wavelengths. Longer wavelengths outside of the visible, the first ones that we encounter are referred to as infrared, or outside of the red, and these we divide in remote sensing between the near and mid infrared, which is reflected infrared, not thermal, and then the thermal infrared, which starts out around 0.8 or so in the 8 micrometers in the electromagnetic spectrum. Now, we also are concerned somewhat with radiation in the microwave part of the spectrum. This is where radar energy that's used for radar sensing resides on the spectrum. As energy from the sun reaches the atmosphere, not all of it. This is a more or less an abstract curve here that is an approximation of what we think the radiation at the top of the atmosphere looks like coming from the sun in terms of its energy content. And as that radiation reaches the atmosphere, different things happen to it. It's either absorbed or reflected, or it's transmitted through the atmosphere, more or less like a transmission through a liquid. And there are different parts of the spectrum that are transmitted, and so these selective windows, and they're selected by the characteristics of the atmosphere, a quote-unquote clear atmosphere. These selective windows are the locations, the wavelength locations on the spectrum where we do have access to to energy to be able to sense it. If we were to look at this part of the spectrum, for instance, if we were to look with our instruments there, which we can do, we can make instruments that are sensible at this part of the spectrum, we wouldn't see anything because there's no energy that makes it through the atmosphere to the Earth's surface to to be reflected. And then this gives you some idea of the different scanners and sensors that we have available to us of their wavelength ranges. We also work by and large in a GIS environment, and this is an illustration that shows an example of how you have these layers, different channels that come from different discrete parts of the spectrum, and their varying resolutions. Here you can see a 30-meter resolution pixel, and then what appears to be a 120-meter resolution thermal pixel, and then a 15-meter panchromatic pixel. This would be channel 8 in the ETM plus. And then all of these are 8-bit data, and so when you look at this, you have 1, 2, 3, 4, 5, 6. There's 48 bits of data. That really is an incredible amount of information in a single pixel across those several channels, just in the multispectral channels 1 through 5 and 7 in a thematic map or image. So this is something that we're thrilled to have all of these data, but one of our problems is to reduce this to a usable piece of information, right? And so the Landsat satellite and the Landsat program is what we use mostly for our work that we do in this class in Remote Sensing 1. And Landsat is the most important data set on global change ever. I mean, it's just an absolutely amazing data set covering the planet from every 16 to 18 days since 1972. Everything that happened since 1972 on the surface of the Earth, pretty much, we can see with this project. We can see it. It's there. You have to look hard for it sometimes, but it is there. Okay? And so the Landsat 7, this is the enhanced thematic mapper. We now are just waiting breathlessly on Landsat 8 and its added channels, but the Landsat 7, as you can see, has 7 multispectral channels and then 1 panchromatic channel. Now this satellite, is similar to Landsats 4 and 5, so really starting from about 1982, this is the type of data that we have available to us from 1982 through the present day. We're waiting on Landsat 8, which will have even more channels and perhaps, certainly greater spatial resolution as well. So this is something that that we're very excited about. So one of the things that really makes this work for us is the selective reflectance characteristics of different types of land cover. This diagram shows you an example of 4 different types of land cover: dry bare soil, gray-brown, or dirt, vegetation, just generic vegetation in green, clear water, and then turbid water, muddy water, right? And so this gives you a sense across the visible and the near and mid-infrared of how the reflectance of these different types of land cover varies. And so you can see there's the relationship as you move across the spectrum, the relationship between these different types of land cover changes, right? And so depending on where you look in the spectrum, you're going to see different things. And really, again, this is just 4 types of land cover. So actually, there are a lot more that we're interested in that we want to look at there. There's so much variation, on Earth that we really have a very daunting task in remote sensing. So again, always look back to this diagram. If you don't know where you are, look back in this and figure out where you are, because you're always working somewhere within the framework of this diagram by and large.